Okay, guys, so we are picking up. We have gotten to the point where we've introduced our orbitals that were derived by Schrodinger and quantum mechanics. So now we want to start taking electrons and start figuring out how the electrons, like how we organize them into the orbitals. There's a few rules that we have to follow. I think the easiest way is to just start working it on the board. So I'm not going to follow the PowerPoint for a little while. I'm just going to talk through the process. And then after that, we'll go back and kind of pick up some details from the PowerPoint that we need. So when we start putting electrons into an atom, we always put the electrons into the lowest energy orbits that we can. So we start with the orbitals that are closest to the nucleus, which we call that the first shell, or we call it the first energy level. In the first energy level, because you're so close to the nucleus, there's not a lot of room there. So really when we have one orbital, it's going to be an s orbital. So we call it first shell s orbital, or 1s. Now as I go up in my diagram, that's going to be increasing energy. So I start at the bottom with a 1s orbital, and whether I put a line or a box or a circle doesn't really matter that much, but that orbital can hold 2 electrons. Okay, once it has 2 electrons in it, no more electrons can be in that orbital, so then any additional electrons will have to go into the next orbital as I go up. Okay, now when I write an electron, there's a very specific way we write it. An electron is going to be a line with half an arrowhead. Okay. Now this is specific that when you go to organic chemistry in a couple of semesters, in organic there's just a notation that when you put an arrow that has a full, like both sides of the arrowhead on it, that represents a pair of electrons. 2 electrons that are moving and forming a bond or breaking a bond or whatever. So since they use that notation for 2 electrons, if we take off one side of the arrowhead and make it just a half, that's 1 electron. Okay. Now I will say the book and other websites may not always be consistent. So sometimes there may be some sources you look at where this is 1 electron and they don't use the half head at all. Don't worry about it too much, but I like to do it the way that you're going to see in organic chemistry. So let's just say I have a hydrogen atom. A hydrogen atom only has 1 electron. So that electron is going to go into the 1s orbital. So I'm going to put an arrow with a half head. That tells me there's 1 electron in the first shell s orbital. Okay. Now, if I had a helium atom, helium is element number 2 on the periodic table. So it would have 2 electrons, and again, we're assuming, unless told otherwise, we're assuming the atom is neutral. So the number of protons, the number of electrons should be the same. So helium has 2 electrons. So if I have 2 electrons in an orbital together, one of the rules we follow is that 2 electrons in an orbital will have opposite spin. The way the electrons spin, which when electrons spin, it creates a magnetic field. Blah, 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 that can affect some of the properties of the atom, but we know that electrons in an orbital together have to have opposite spin. So I'm going to represent that by putting the second electron where the arrowhead is pointed down. One is pointed up, one's pointed down. That just represents the opposite spin of those two electrons. All right, once I put in 2 electrons, the first shell is full. Okay, whenever I get a full shell, that actually is a very stable arrangement of electrons. So that's why the noble gases are always going to have at least an important part of their highest shell that they're in is going to be full. And that full set of orbitals is what makes it so stable. That's why noble gases don't really make bonds most of the time, because they don't want to gain or lose any electrons. They want to stay the way they are. Okay, so that's the electron diagram. Electron orbital diagram for helium. All right, now let's say we go to carbon. Carbon is element number 6, so it has 6 electrons. Well, the first 2 are always going to go in the first shell s orbital. Like that's always where I start. Once I fill that up, then I have to go further out from the nucleus which if I go further out from the nucleus, the orbital energy levels are going to be higher. We're going to get to the second shell, or what we call the second energy level. It's bigger, and every time I move to a new shell, I'm going to introduce a new type of orbital. Okay, so in the first shell I had an s orbital. In the second shell, I'm going to repeat the s orbital and then add the next type, which are p orbitals. Okay, so I go up, the 2s orbital. Again, that orbital, just like the 1s, but it's bigger. But even though it's bigger, it still only holds 2 electrons. Then I can do the 2p orbitals, which the 2p orbitals are about the same distance out as the s orbital, a little bit further, but they're in the same range. But technically, the 2p orbitals are slightly higher in energy than the 2s. So I'm going to put the 2p a little bit higher than the 2s. And remember when we said p orbitals always come as a set of 3. So there are 3 distinct orbitals that come together, and they have the same energy. So those 3 are the 2p orbitals. Now, if you remember, we talked about they're kind of shaped like dumbbells, but each one is perpendicular to the others. So one of them I could say is oriented on the x-axis, one's on the y-axis, and one's on the z-axis. Okay? Each orbital can hold 2 electrons. So I can put 2 here, I can put 2 here, I can put 2 here, 2 here, 2 here. So up to this point, if I fill all these up, that would get me up to 10 electrons. Okay? Well, carbon is the one I said I want to do. It has 6 electrons. I'm going to work my way from the bottom up. So I've already put my first 2 in there. Then I put number 3 right here and number 4 right there. So I'm up to 4. Now for number 5, I filled up my 2s. Now I got to go to 2p. Again, which one I start with doesn't really matter. They're all equal to each other. There's a word that's used. They are degenerate, which means they're equal. The energy for an electron in any of those orbits is going to be the same. So it doesn't really matter which one you put it in. Most people like to work their way from left to right. So at least initially, I'll just put the first electron right there. So now I'm at 5. There's another rule that we have to follow. If 2 electrons in an orbital together, they're going to have opposite spin. But if I have a choice to spread the electrons out, they don't want to pair up unless they have to. Remember, electrons are all negatively charged. Similar charges repel each other. So electrons don't want to be in the same orbital if they can avoid it. So I put 1 electron in this orbit. My next electron is going to go into a different orbital. So I'm going to put it right there. Okay, so those 2 electrons want to be as far away from each other as they can. Now sometimes students say, well, if it wants to be further away, why don't I put it over here? Well, remember these 3 they're all perpendicular to each other, x, y, and z axes. So really any 2 of them are all 90 degrees apart in terms of how they're spaced apart with angles. Okay, so it doesn't matter which 2 you put it in, but the key is the first 2 electrons that go into the p orbitals have to go into separate orbitals. So that would be the electron diagram for carbon. Okay, now let's keep going. Let's say I have magnesium. So if I have magnesium, if you look at the periodic table, that's element number 12. Okay, so I'm going to move on. The first 6 are going to go just like this, but now I'm going to keep going until I get to 12. So I'm doing magnesium. So I got 6. Number 7, again, if I can spread these out, I'm going to put number 7 right there. Then finally, number 8, now I don't have anywhere else to put them. I have to start pairing them up. So I don't pair them up until I have to. But once I've got 1 in each, now's the time I have to start pairing. So it's going to be number 9. No, excuse me, that's number 8, number 9, number 10. And then at that point, my second shell is full. So now I have to go further out from the nucleus. Now I'm going to get into the third shell. When I go to the third shell, again, it's higher energy. I'm going to be further out from the nucleus, and I'm going to introduce another set of orbitals. So this time I'm going to have the 3s orbital. I'm going to have the 3p. And I'm going to have the 3ds. Now, notice the pattern. The S always comes by itself. The P's are always a set of 3. The D's are a set of 5. Each orbital can hold 2 electrons, and I don't pair them up until I have to. Okay, so right now I have 10 electrons. So I'm going for magnesium as 12. So I'm going to put the next 2. That's number 11. That's number 12. Okay, so that's my electron diagram for magnesium. Next thing, what if I don't want to draw this whole thing out? Is there a way to kind of summarize this in a cleaner fashion? And the answer is yes, there is. Once we kind of have an idea of what the diagram looks like, we can write a summary that's called the electronic configuration. Okay, and then basically I'm gonna list, going straight across, I'm gonna list all the stuff that I've done there. So I would look at it and say, okay, what was the first thing I did when I started? I had the 1s orbital, and then the number of electrons that I put into that orbital is going to be a superscript. So it's 1s orbital with 2 electrons in it. That's going to be the 1s2. What did I do next? Then I went to 2s and I put in 2 electrons. So that's going to be 2s2. Then I went to 2p's, and as a group I put 6 in there. So that's going to be 2p6. And then finally I went to 3s and did 3s2. So this is a summary of what's in my diagram. Okay, most of the time we initially learn the diagram to kind of see the relationships and why I work my way from the bottom up. This gives me the order that I fill the order that I fill up the orbitals. But once I have that down, this is a much quicker and cleaner way to write it. So most of the time I would say write the electronic configuration, and this is what you would write. Okay, so now we're going to keep going. I did magnesium. So that took us up, and we got into the 3rd shell. Let's imagine we're doing an element in the 4th shell. Okay, so this time we're going to do bromine. Bromine is number 35. Okay, well, number 35 electrons, it's going to take me through all the 3rd shell, and I'm going to actually get into the 4th shell. Okay, now when we get to the 4th shell, again, it's going to be, the 4th shell will be generally set higher than the 3rd shell. It's further out from the nucleus. I'm going to introduce another type of orbital. So I'm going to have 4s, 4p, 4d, and 4f. But one thing that's really important, even though the 4th shell energetically is mostly higher than the 3rd shell, it's not going to be as separated as we think, and actually the lowest orbital of the 4th shell will be underneath the highest energy of the 3rd shell. So more specifically, when I start the 4th shell, my 4s orbital is going to be less energy than my 3d orbitals. So I'm actually going to put my 4s, if I come down just a little bit, it's less energy than 3d. So I'm going to do 4s, then I'm going to have my 4p's, then I have my 4d's, and then I'm going to have my 4f's. Okay, so now I have all those orbitals, and when I open up the 4th shell, all those orbitals are there where I could put electrons into them, but I work my way from the bottom up. So right now, up to here, I've got 12 electrons. I'm going to go all the way to 35. Okay, so take a minute, see if you can do that yourself, but then I'm going to start filling them in. So from 12, I'm going to go 13, 14, 15. I put 1 in each. 16, 17, 18 fills up the 3 P's. Now if you notice, every time I fill up the P's, I get that's a noble gas. Neon is number 10. When I get to 3P, that's argon. Okay, and again, that's going to be important in the next step that we go to. So I got through 18, and then number 19 and 20 go into 4S because it's lower in energy than 3D. You always work your way from bottom up, so 4S comes before 3D, even though that we think the 3rd shell should be filled up before the 4th shell, but they calculate how much energy the electron takes in any given orbital, and you have to work your way from bottom up, okay? So I'm at 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. Notice I put one in each before I put the second one in each. So I'm at 30 now. Bromine's number 35, so I'm going to go to the 4 P's. 31, 32, 33, 34, 35. So essentially bromine has the 4P with 5 electrons in it. So if I write my configuration, that's going to be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p5. That's the configuration of bromine that I would want to write out. Now, that's what we call the full electronic configuration, or we sometimes call it the spectroscopic notation. Basically, it shows everything. There is a shortcut. If we look where the noble gases are, we can use what's called the noble gas configuration, which essentially is when we study an atom and its properties, most of the properties are going to be controlled by the last set of electrons that we have. They're going to be called the valence electrons. We only really need to see those. A lot of the earlier ones are in lower shells. They're really close to the nucleus. They're not really part of bonding as much, so we don't really need to see them as much. So when we do the noble gas configuration, we're going to hide the lower energy orbits that we call those the core electrons, and we're only going to show the outer ones. So you have to use the last noble gas, which was argon. That represents everything up to 3p6. I'm going to write argon in brackets, and then I'm going to say 4s2, 3d10, 4p5. I have to show everything that comes after the previous noble gas. That's going to be my noble gas configuration. When we get down near the bottom of the periodic table, it's a lot easier to do that than the other way. I'm going to cut off and we'll keep going in the next video.